Thank you, Chairman. Hello, everyone. I'm Soobeom Lee. Now I am working as a postdoctoral fellow at DGIST in Republic of Korea. Today, I talk about electric double layer modulation of spin orbit torque efficiencies in platinum, cobalt, platinum trilayer. Spin orbit coupling is a relativistic coupling of an electron spin with its momentum in a potential. The so-called spin current is electrically generated via spin orbit coupling. We now suppose a bilayer of spin orbit material and ferromagnetic material. If spin current is electrically generated in spin orbit material, then a part of spin current is observed to adjacent ferromagnetic material. Angular momentum of spin current in ferromagnetic material exerts a torque on magnetization. Actually, the spin orbit torque is widely applied in magnetization switching and domain motion. Therefore, spin orbit torque is essential tool to electrically manipulate magnetization. Until now, much effort has been devoted to spin orbit torque engineering, almost by modifying film structure, such as partial oxidation of a ferromagnetic layer, annealing the film, sub-nanometer intercalation, and alloying, and so on. In these methods, however, spin orbit torque could not be controlled anymore after the device fabrication. Meanwhile, dynamic control of spin orbit torque provides a novel function for future spin orbit torque devices. We now change the topic from the spin orbit torque to electric double layer. Recently, electrolyte has been attracted much attention for electric gating. If we apply the gate voltage between gate and channel where electrolyte is sandwiched, cations and anions in the electrolyte are polarized. Subsequently, accumulated cation in the interface induces accumulation of counter charges in the channel. In here, the structure of anion and cation and counter charge is called as electric double layer. Because the gap of electric double layer is atomically narrow, it possesses high capacitance density and large strength of electric field can be applied. Namely, electric double layer induces a large surface charge doping. Furthermore, much larger gate voltage application can induce chemical reaction. Actually, previous reports has demonstrated electrical engineering spin orbit coupling in single platinum layer using electric double layer. Dr. Dysenko reported gate T-number inverse spin Hall effect in 2 nanometer thick single platinum film. And Mariyama also reported that gate modulation of Harlem magnet resistance in 1.5 nanometer thick single platinum film. Following the previous researches, we are now curious if it is possible to electrically tune the spin orbit torque using electric double layer. So in this study, we aim to electrically modulate spin orbit torque efficiencies using electrolyte gating in perpendicularly magnetized platinum cobalt platinum trilayer system. Let me introduce the device structure and the measurement sequence. We fabricated a whole bar device of 2 nanometer platinum, 1 nanometer cobalt, and 1.5 nanometer platinum with 0.5 nanometer tantalum seed layer. And here, tantalum seed layer was grown to enhance crystal quality and perpendicular magnetic anisotropy. To apply gate voltage, we drop a compound of electrolyte and a polymer. The electrolyte is originally liquid phase, but it is scaled by adding the polymer. Gate voltage is applied in the range of plus minus 2 volts with a scan rate of 5 millivolt per sec at room temperature. So in this device, we first conducted conventional DC for terminal measurements at room temperature, and then performed harmonic core measurements at 200 Kelvin with electric gating. We now demonstrate the gate-controlled electrical resistance of platinum-cobalt-platinum core-bar device. Electrical resistance is measured in conventional DC 4-terminal measurement. As you can see here, electrical resistance of the pristine device is about 530 ohm, and it is decreased under the applied positive gate voltage, and it is increased under the applied negative gate voltage by electron deflation accumulation. Here, hysteretic behavior is a characteristic of electrolyte. Due to very small ionic mobility, ions are spontaneously polarized even after turning off gate voltage. After 2 cycles of gate voltage application, resistance is still higher than pristine resistance. It means ions are still spontaneously polarized. We were able to modify the resistance by more than 10% even in a metallic system. We also note that such a resistance modulation could not easily achieved using the conventional solid gate. Following the gate modulation of electrical resistance, we conducted harmonic Hall measurements. As you probably know, anomalous Hall effect in Hall device is contributed by out-of-plane spin components. If we apply AC current in ferromagnetic layer and heavy metal structure, perpendicular magnetization is vibrated by AC spin orbit torque. Then the measured Hall voltage could be theoretically derived, and here second harmonic signal is contributed by spin orbit torque. And namely, the strength of spin orbit torque can be quantified by measuring harmonic Hall voltages. Sequence for harmonic Hall measurement is as follows. First, we apply gate voltage at 300 Kelvin and cool down to 200 Kelvin to suppress leakage and shunting currents in electrolyte. And we carry out harmonic Hall and other DC measurements. Finally, warm up to 300 Kelvin, and once again, gate voltage is applied. There are typical second harmonic signals on the various gate voltage application. We successfully obtained the second harmonic Hall signals as a function of applied external magnetic field. From the linear slope of second harmonic signals, with planar Hall correction, we can extract the effective fields of damping-like and field-like spin orbit torques. Here we show the current density dependencies of the extracted effective magnetic field under applied gate voltage of 0 and 1.8 volts. The effective fields of the damping-like spin orbit torque are significantly modified when the gate voltage of 1.8 volts is applied. However, unfortunately, when the negative gate voltage was applied in sequence, reversible gate modulation of resistance and effective magnetic fields was not achieved. We guess that electrolyte was deteriorated due to very long-term measurement. From the effective magnetic fields of spin orbit torque, we next calculated spin orbit torque efficiency using the following equation. Even though gate modulation of spin orbit torque was not reversible probably due to the deterioration of electrolyte, we can clearly see the relation of spin orbit torque efficiencies and the resistivity. Maximum minimum ratios of damping-like and field-like torque efficiencies are 290% and 240% respectively. According to damping-like torque efficiency, it is contribution of the spin Hall effect in platinum. So we can expect that damping-like torque is canceled out at the low resistivity, and damping-like torque from bottom layer is dominant at the high resistivity. And next, we suggest the possible scenario of damping-like spin orbit torque modulation. As previous research claimed, the Fermi level of platinum is shifted by electron doping via ionic gating. Then, Depending on the d-band structure of platinum, intrinsic spin Hall effect could be modified because it is dominated by inter-d-band transition. To verify the above hypothesis, we calculate the resistivity dependence of a spin Hall angle in top platinum layer using following theoretical model. The model is constructed based on spin diffusion equation and very simple non-magnetic, ferromagnetic, non-magnetic trilayer is considered. To simplify the calculation, several rough assumptions are introduced, such as transparent interface with a spin memory loss, isotropic spin relaxation in ferromagnetic material, and the whole top layer is affected by electric gating. By calculating the boundary conditions, we derive a spin current in ferromagnetic layer. Furthermore, spin torque efficiency is described by the following equation. We extract the spin Hall angle from experimentally obtained damping-like torque efficiency at each resistivity. Though several rough assumptions and parameters are introduced, we find that the gate modulation of damping-like torque could be described by the modification of spin Hall angle in top platinum layer. To summarize, electric double layer modulates resistance and spin orbit torque efficiencies in perpendicularly magnetized platinum cobalt platinum trilayer. Gate modulation of damping-like spin orbit torque is ascribable to modification of spin Hall angle, a spin Hall effect in the top layer. The deterioration of the ionic gating would be ascribed to the very long time measurement. Okay, thank you for your attention.
Thank you for the talk. So let's move on to the question time. Does anyone have a question or comment? If you have, please raise your hand, and I will unmute you. Okay, so let me ask you something. So please go to the result of the I mean the gate voltage depend
here.
Please go before. So I want to ask about the oh yeah, here.
Okay.
Minus gate voltage. So are you using the ionic gate film, right? Ionic gate light.
Yeah, right. Yeah.
So after removing the ionic gate, did you measure the same measurement, and the result will be was the same with the voltage?
Oh yes. Actually, I didn't try, but you're right. If so, you mean you want to know either it is chemical effect or electrostatic effect, right?
Yeah, I'm concerned about that. So yeah, that's why I asked. Yeah.
Actually, I didn't try, but that's a good idea.
Okay. Yeah, I would suggest you.
Thank you.
Okay, is there any other questions? Okay. So yeah, let's